So far, our discussion of polynomials has focused on end behavior and x-intercepts, what happens at the ends of the graph of our function, and what happens in the middle, particularly at the roots, the zeros, or the x-intercepts. Ultimately, our goal is going to be able to sketch a graph of a polynomial given its equation. And this is something that we'll get to in the next video. But first, in order to connect the ideas of end behavior and x-intercepts and graph all of this stuff in between, we're going to need to talk about continuity, smoothness, and the intermediate value theorem. Now, these are all ideas that will be explored in much more detail in a calculus course. But at least for now, we'll start to build a little bit of an intuition, and albeit informally, we'll define these concepts in a way that we can utilize to help us graph polynomials. These three concepts will give us a more concrete way to literally connect the dots as we plot our points of the x-intercepts and explore our end behaviors to graph our full polynomial functions. And so let's start with smoothness. Now again, this is a concept that will be explored formally in a calculus course, but at least in terms of the intuition, we can really think of smoothness as any graph that doesn't contain any sharp points or corners and is only featuring smooth rounded curves. In other words, a smooth graph is one that contains only rounded curves with no sharp corners. And specifically to illustrate this, we can think of comparing and contrasting the graphs of y is equal to x squared with the graph of y is equal to the absolute value of x. Now, both of these graphs have a vertex. However, specifically on the left here, this vertex occurs at a rounded curve. And so we would say that the function y is equal to x squared is smooth. The absolute value of x, on the other hand, comes to a point. It has a corner. And so we can recognize that the graph of the absolute value of x is not smooth. Then we would say that a function is continuous. A function is continuous if its graph has no breaks. In other words, it can be drawn without lifting your pencil. It can be drawn without lifting your pencil. And so, for example, I could draw something like this. And because I can draw the entire curve from start to finish without lifting my pencil, it is continuous. There exist no breaks along this graph. In contrast to this, on the right here, if I was to draw something like this, this would represent a discontinuous function, or a function that is not continuous. Right? At this point here, we have a discontinuity. The function doesn't continue straight through. It goes up to that point, has a break, and then continues elsewhere. The fact that we see this break here, that's what tells us it's not continuous. And in our study of functions so far, we've most commonly seen this in piecewise functions, for instance. And as these concepts relate to polynomials in particular, the important thing to note here is that all polynomials have both of these characteristics. In other words, all polynomials are both smooth and continuous. And this is important because both of those features make this a lot easier for us to understand them and a lot easier to graph. Right? If we don't have to worry about sharp corners or breaks, that tells us a lot more information about how we can connect the dots as we draw the graph of our polynomial functions. In particular, these two characteristics of polynomials allow us to formally state some important information about the existence of roots for these types of functions. And this will be what's known as the Intermediate Value Theorem. And what this theorem states is that for a polynomial function, f of x, if f of a and f of b, so 2 points along our graph, have opposite signs, in other words, one is positive and the other is negative, or vice versa, then there is at least one value, which we'll call C, that lives between A and B, so between A and B, for which f of C is equal to 0. And so if we imagined a graph where our horizontal axes is our x values and our vertical axes is our f of x values, and selected 2 points A and B, where one of them maybe was negative and one of them was positive, we would guarantee that there had to be some value in between, so something in here, some value C, where our polynomial has to cross the x-axis, where we have to have a root, where we have to have an x-intercept. So in other words, there exists a 0 between A and B. And the reason for this, because all polynomials are continuous, we would have to draw them from this point to this point without picking up our pen. In other words, there can be no breaks. So if we were to do that and draw our curve up this way, then no matter what it did, if it was going to make it up here to B, it's going to have to pass at some point through the x-axis, right? We can't have the function break like this because then it would be discontinuous, and we now know that all polynomials are continuous. So regardless of what it does, as crazy as it might get here, at some point it's going to have to cross through the axes in order to get up to the other side to reach the point f of b. And if you're sitting in any doubt of this fact, try exactly this exercise here where you start at an f of a below the axes and finish at an f of b above the axes, and try to draw a polynomial function without picking up your pen from one point to the other that doesn't cross the x-axis. And although really just an intuitive proof, you'll convince yourself of this pretty quickly. And this is what we call the intermediate value theorem, because kind of as the name suggests, there is a value in the middle, the intermediate value, between an f of a that might be below the axes versus an f of b that might be above the axes. So there is a root somewhere in between. And now this theorem will be useful for a lot of things, including informing how we can graph these functions, which we'll do in the next video. But for now, what we can do with this is prove the existence of a root on some given interval, where the values of the function at the endpoints have opposite signs, either one positive, one negative, or one negative, one positive. And so if we look at the function f of x equal to x cubed minus 3x minus 1, we'll be able to prove that this has a 0 between x equal to negative 2 and x equal to negative 1 simply by using the intermediate value theorem. Now again, what the intermediate value theorem says is that if f of a and f of b have opposite signs, in other words, one is positive and one is negative, then there exists a root. So there's a root between a and b. And so if we evaluate our function f of x at these 2 points and they have opposite signs, then the intermediate value theorem will guarantee the existence of a root on the interval from one to the other. And so what we can do first is evaluate the function at those 2 values. So if we look at negative 2 first, we can plug in negative 2 for f, giving us negative 2 cubed minus 3 times negative 2 minus 1, which as we evaluate will be negative 2 cubed, or in other words, negative 8, right? Negative 2 times negative 2 times negative 2 gives us 8. And then we have minus 3 times minus 2, or in other words, plus 6. Those 2 negatives make a positive. And then minus 1. Negative 8 plus 6 will be negative 2, and negative 2 minus 1 will be negative 3. And so since it's negative, what we're going to want, if we're going to be able to prove there's a root, is for the value of our function at x is equal to negative 1 to then be positive. And so let's see if we actually have that. If we find f of negative 1, we can plug negative 1 into our function and get negative 1 cubed minus 3 times negative 1, minus 1. Here, negative 1 cubed is going to give us negative 1. Minus 3 times minus 1 will become plus 3, and then we carry down the minus 1. Doing the arithmetic, minus 1 plus 3 is going to give us 2, and 2 minus 1 is equal to 1, and indeed we do have a positive number. And so because f of negative 2 is below the x-axis and f of positive 2 is above the x-axis, the only way we'll be able to get from one point to the other without picking up our pencil, which must be true because all polynomial functions are continuous, would be to cross through that x-axis. And so since f of negative 2 is less than 0 and f of negative 1 is greater than 0, by the intermediate value theorem, which we'll just abbreviate IVT, by the intermediate value theorem, there exists a 0 between x equal to negative 2 and x equal to negative 1. And if we take a look at the graph, we can see this here. At 2, negative 3, we are below the x-axis, and then the only way to move up to negative 1, 1 would be to cross through the axes at this point here, at this 0. And so I hope you found this video helpful, and hopefully it gives at least a little bit of a preview or insight into some of the ideas that we might discuss a little more formally in a calculus class, and also a little bit of a preview into what we might think about or what tools we might use to inform how we're going to connect the dots of our polynomial functions in the next video, where we put together the ideas of end behavior, continuity, and roots and intercepts. As always, please reach out if you have any questions. Otherwise, I hope you have a great rest of your day.